so although this talk would be a very entry-level talk, but I hope I can bring you something. The first one, when you build a strategy, keep remind yourself about the issue of overfitting. And the second one, I will introduce a new approach to quantify the probability of backtest overfitting. And the final one, I will show some Python package. I show some Python package when you want to do some financial analysis. It will be very useful. Okay. Okay, there are millions of ways to avoid backtest overfitting, but actually today I will only focus on a new one. So and compare it to other approach. So to be more precision, I think the topic I would like to share is a new way to avoid backtest overfitting when building a strategy. Okay, let's recall the overfitting. If I can draw your attention to this figure, you can see that the model in the right-hand side is significantly overfitting model, and the overfitting model have no prediction power to predict the future. Okay, so let's look at the problem when you build a strategy. When you build a strategy, you want to make sure your strategy capture the signal or the noise. Okay, so some historical pattern is a natural phenomenon, and some are random pattern. Okay, so when we build a strategy, all we want is to capture the natural phenomenon, but sometimes we just fit the noise, and thus overfitting happen. Okay, so I want to point out the overfitting of strategy selection. Okay, so nowadays many invest firms rely on backtest to calibrate their parameter or optimize their strategy selection. But if you choose your strategy only by the backtest, you may in the danger of backtest overfitting. Okay, so now we can look how does the backtest overfitting look like. Okay, in this figure, you can see the green line is the underlying target. You just think of it as a stock price, and the blue one is your strategy. If you choose the best strategy from the in-sample, if you have 100 strategy on your hand, and then you choose the best one from the in-sample data, then you might get a strategy. Its performance is very perfect, just grows stably, and you seem to earn money very easy. However, if backtest overfitting happen, then actually when you use the same strategy on the out-sample data, you will see your profit and loss will look like the blue line. Yeah, you will lose money. So, so you might want to ask, is there any approach to quantify the degree of backtest overfitting? Yes, there is a working paper to estimate the probability of backtest overfitting, and it is a very new paper. The latest version is released in February this year. Okay, so I noticed this topic is because it's one of the topics in the R Finance Conference Chicago last year. And I think it deserves to share with you because this paper also released some application in Python language. And for me, I think this approach is very valuable because it's very intuitive, easy to understand, and it's easy to apply to any strategy selection process. Okay, so firstly, we need to define what is the backtest overfitting. Okay, you can see there are some mathematical formula. If you don't like mathematics, you just can skip it. we can think of, I told you the intuition of the backtest overfitting in this paper. Okay, think of a situation if your strategy selection process is not overfitting, then your optimal in-sample strategy should also outperform most of the strategy out of the sample. But while if your strategy selection process is overfitting, then it's more likely to underperform most of the strategy out of sample. And here we define the most of strategy to be the 50% strategy. Okay, so then I'll give you a simplified definition of backtest overfitting in the middle part. Okay, it states that the rank of optimal in-sample strategy is worse than 50% strategy when you evaluate it out of the sample. Okay, so it's the backtest overfitting definition in this paper. Okay, I need to clarify that the overfitting I mentioned here is for the strategy selection process instead of the model calibration. Okay, so I will quickly go through the procedure implement in this paper. Okay, it's a combinational symmetric cross-validation procedure. Okay, there are 6 steps to go over this procedure. The step 1 is you need to collect a matrix of profit and the loss time series for each strategy. So if you have 100 strategy, you have to collect 100 profit and the loss time series. And then the second step is you need to split this entire data into some disjoint submatrix. For example, if I choose s equal to 4, then I split the entire data into 4 parts. And here the symbol is M1, M2, M3, and M4. Okay, the step 3 is we want to generate all the combination from this submatrix. So for example, in the first trial, our training set would be M1 plus M2, and while our testing set will be M3 plus M4. And in our second trial, the training set would be M1 plus M3, and the testing set would be M2 plus M4, and so on. Okay, and for each combination, we need to compute the performance of in-sample data and out-of-sample data. And we will find the optimal in-sample strategy and its corresponding out-of-sample performance. The next one will get the rank among all the out-of-sample strategy. And then compute the statistic, here we call lambda here. Okay, and then we can compute the probability of backtest overfitting by this way. It's a number of lambda less than 0 divided by number of lambda. Okay, so I think maybe you are still not clear with this procedure. I'll show you an example with real data, not real data, but pseudo real data. Okay, and thanks for the powerful scientific computing Python package, we can easily implement this procedure. Okay, and okay, this one. Okay, in this ipython notebook, I will show you how to implement this procedure in a very simple way. Okay, and the tool we need in this demo will be pandas, numpy, scipy, and matplotlib and seaborn. Okay, and this package is very popular in the data analysis field. Okay, firstly, you need to collect the performance time series. So suppose we have 100 strategy, and for each strategy when backtest for 10,000 days. And then we generate a pseudo daily return from a normal distribution. So you can see the output for each column. It's a daily return time series for last strategy. So for example, the daily return of strategy 0 in the January 3, 2000 is 0.9 loss. Okay, and it's a, you can think of it as a price plot for I should say it's a NAV for each strategy. Okay, the next one. The step 2, we split all the entire data into 8 disjoint submetrics. Okay, so each data partition with the size to equal to 100 to 25 days. Okay, so here's the output. The partition number 1 will be from this day, and the partition number 2 will be from the June. Okay, so now we have 8 data partition. And then step 3, we generate all the combination of the submetrics. Okay, so here you can say the total trial we have is 70 because if you take four element from 8 combine C8取4要怎么讲？就是 C8取4，就是 so you will have 70 trial. Okay, so you will have 70 trial, and in your first trial, your training data will be partition number 1 and the plot combination of partition number 1, 2, 3, 4, and so your testing data would be 5, 6, 7, 8. And the second trial, your training data will be 1, 2, 3, 5, and the last your testing data will be 4, 6, 7, 8. Okay, it's so on. Okay, next step 2, step 4. We need to compute the in sample and out of sample performance. And here we take the last combination. Okay, so you can see our last combination is 5, 6, 7, 8. So my training set will become combined by these 4 submetric. And my testing set would be the 1, 2, 4. Okay, here is the training set, and here is the testing set. And then here we need to choose a performance measure. And I use a simplified Sharper ratio here. Its definition is the average return minus the risk-free rate divided by the standard deviation of the daily return. And this is mean if I take 1 unit risk in the form of standard deviation, how much return I can get. Okay, so we apply this measure to the training set and the testing set. And you can say for in the in-sample data, each strategy, the Sharper ratio of each strategy would be like this. Okay, and the next step, we need to find the best strategy in the in-sample data. Okay, so the best in-sample strategy is the strategy 76. And the in-sample Sharper ratio is 0.1, while the out-of-sample Sharper ratio is significantly less than the in-sample Sharper ratio. It's only less than 0.01. Okay, then we need to know what is the real performance of the best in-sample strategy? So here we know the best strategy is 76, and its rank in the in-sample Sharpe ratio is 99 because it's the best strategy. While, how about its rank of our sample Sharpe ratio? It's only the 59. So the relative rank of the Sharpe ratio is 0.59. Okay, and then now the final step. We compute statistic called lambda, and it's a log of relative rank divided by 1 minus relative rank. Okay, so here we know that for the strategy 76, its lambda is 0.36, and this trial is less likely to be bad test overfitting because its lambda is greater than 0. Sorry. So why does the lambda less than 0 mean? Okay, we can do some simple calculation. Okay, lambda is equal to this, and if it is less than 0, it does mean if you take exponential for both sides, it will be look like this, and you multiply 1 minus r for both sides would be like this way, and finally you get the relative rank would be less than 0.5. So because the r is the relative rank, so it means the rank out of sample is less than half of the strategy, and this is match our definition I mentioned before. Okay, so we got 70 trials, and so we do the same thing for all 70 trials, and then we will get the output like this way. In the first trial, the number 0 trial, the best strategy in sample Sharpe ratio would be 0.1, and our sample Sharpe ratio would be 0.01, and its lambda would be 0.57. Okay, so because here we know lambda less than 0 is equal to the best strategy in sample is bad test overfitting. So here we compute the probability of bad test overfitting to the here the number of lambda less than 0 divided by number of lambda, and you can see this is a distribution of the lambda, and what is the probability that lambda less than 0 is the left hand side from the red line is this part. It's about 0.6. Okay, so now we can do the hypothesis test. If our null hypothesis would be the strategy selection process is bad test overfitting, and if your probability of bad test overfitting is less than is less than 5%, then you can reject the null hypothesis. Okay, by this CHCV procedure, we can use other tools to evaluate the bad test overfitting. The first one is the probability of bad test overfitting. It's a statistic that we just mentioned, and the next one is the performance degradation and the probability of loss. What does it mean? Okay, we can look at this figure. In the horizon side, horizon axis is the in-sample Sharpe ratio, and the vertical axis is the out-of-sample performance. And you can see that all the in-sample performance is positive, range from 0.06 to 0.18, while the our sample is worse than the in sample, there are much of trial gets a negative Sharpe ratio in the our sample. So we can know that because the linear regression of the slope of the linear regression is negative, we can know that the better your in-sample performance is, the poorer your out-sample performance is. And also we can calculate the probability of loss. You can count how much data behind the 0 and divided by the 70. Yeah. Okay, it's almost a paper say. Okay, so now you might want to ask why we use CHCV procedure. Why not other popular tool like holdout approach? Okay, holdout approach has some disadvantage. Like if your data set is very small, it's not practical to split a small data set into a smaller one. And for some performance measure, you can compute a reliable measure when the data set is too small. And number two, if you use a different holdout, you will get a very high variance output. And the number three, when you use holdout, you will hold out the latest data or the earliest data. Okay, if you hold the last data, and you will lose the most important information when you train your model. So, but if you hold out the earliest data, then you will test your performance by using the data that you don't really care about. Okay, and the holdout does not prevent the overfitting because as long as you run enough time, you can find a parameter that is both overfitted in sample and by luck your out sample has the same random pattern. Okay, so why we use the CHCV procedure? How's its advantage? The first one, you can control your sample size of the in sample and the out sample. They will be equal. So if you use some performance that is very sensitive to a sample size, then you can use the lib1out cross validation because the sample size for the training data will be very large, and the testing set of the sample set of the testing set will be very small. Okay, and I think the most important is that the CHCV procedure would preserve the important pattern of financial time series. Because most of financial time series are series correlated. So if you use the K4 cross validation, you might to random shuffle the data. I mean the lib1out cross validation, because you will shuffle the data, so you can preserve the order of the financial time series. Okay, and if you use the CHCV procedure, you can get the same distribution of logit. If you run this procedure twice, yeah, the output will be the same. And then you can also use the distribution of logit to check your strategy selection process is robust. Yeah, because if the variance of your distribution of logit is very small, then it means you will get a very similar result over each trials. Okay, and the final one is I think it's very important. because this procedure is model-free, so it's easy to implement on any strategy selection process. We don't need to know the trading rule. We don't need to know the forecast equation, and the only thing we require is the performance time series. Okay, and also this procedure has some limitation. Although this procedure does not shuffle the data too much, but if you choose a performance measure that is too sensitive to the order, that would be that would be not good. And this procedure is assume each strategy has the same weighting. So if you know the weighting of each strategy would be select, you can implement a weighting into this procedure. Okay, finally, in this paper, it gives us some practical application. Okay, we think of a strategy like that. You want to build in a strategy to profit from the seasonal effect. So you buy a stock in, for example, you buy a stock at every 4th day every month, and holding for 3 days. And if the stop loss, and if reach 3% loss, you will stop loss. So in this simple strategy, you will have 4 parameters. One is buy or sell, and the other is the entry day. You can entry in the 1st day of the month or the 2nd day of the month. And the 3rd parameter is how long will you hold your equity. And the 4th parameter is a stop loss. Okay, you can find the code here. The author, okay, you can see that. Okay, the author put his code in here. Yeah. Okay, you can take a look of it. Okay, and let's discuss 2 cases. The first case is that it generates the underlying target stock, and it returns from random walk. So actually, there is no pattern in this pseudo daily return, but it still fits the same strategy. Okay, so you can see that the strategy is also the blue line. But we know actually the underline has no signal, so we know this strategy is overfitting. And for this strategy, is distribution of logic look like this, and the 0 is at here. You can see the probability of overfitting is this part. It's 55%. While the second case is we also generate a return from the random walk, but we manually modify the first 5 days to the same variance. So there is a pattern here. And thus the distribution of logits looks like this way. The 0 is here. So you can think that this strategy selection process has less probability of beta overfitting. It's only 13%. Okay, so this procedure provides a very simple approach to quantify the beta overfitting. Okay, and that is all. Thank you for your attention.
Does anyone has questions? Do you have any example or practical example about that this kind of method better than cross validation? Because cross validation is average of rows, and this kind of it's average of like maybe some kind of ranking in about in sample error and worse than out sample error. Do you have any practical example about that this would be better than cross validation?
No, I don't have, but I will implement this procedure next Monday because I have no time to prepare a practical example today. 对, but I think it's very easy to implement to the strategy in our company. So I will try it.
Okay, does anyone has questions? Okay, I guess that's it, and let's thanks Yen.